Hey guys, here's a video on refraction. What are we going to cover today? We're going to find out when light actually does refract. In other words, what is it? What causes it? There's a trick that we can learn to figure out what direction light will refract. We'll learn about that. And then total internal reflection, which turns out to be very important to our communications and our modern technology, and it will be significant in a future unit. So this is a key element of this unit, and a large part of the reason we're studying it at all. And then finally, we're going to look at the phenomenon of gradual refraction, which you may find interesting. So starting off, what is refraction? Now obviously this is not some horrible physics accident. We know from experience that the guy's head is still attached to his body. It just looks distorted because we're looking into the pool from an angle. And again, from life experience, we know that tends to distort images. The light changes direction under certain circumstances, which is what refraction is. So what is it? Refraction is the bending of light as it passes from one medium to another. And the reason this happens is because the speed of light is different in different substances. So for example, in air, the speed of light is almost exactly the same as it is in a vacuum. Because the space between air molecules is relatively large. So as far as the light's concerned, it's mostly going through vacuum and occasionally running into an air molecule. But when the light goes into water or a block of glass or plastic or something like that, then the molecules are much closer together, and that slows light down significantly. So the speed of light is slower in different mediums, and that change in light causes the light to change direction. So this is a little bit complicated here. This is the rule that we're trying to remember and understand. This is the idea that light bends toward the normal as it passes into a substance with a slower speed of light. So what is a normal? Well, you remember normal force, and normal force is a force that acts perpendicular to the surface that produces it. So it goes straight up from a table, it goes straight horizontally when you lean against a wall. That's a normal force, and normal in that context means perpendicular to. So the normal in this context is a reference line which is perpendicular to the surface that the light is passing through. So in this case, we have a light ray which is entering this transparent plastic block, and our normal is a reference line which is perpendicular to the surface of that plastic block. Now there's some good reasons that we do it this way that don't really matter to us today, but that's just how we do it. So when light comes in from air, where the speed of light is fast, and it enters the plastic block where the light is slow, it bends toward the normal, toward this vertical reference line. It bends toward the normal as it passes into a substance with a slower speed of light. Now, when it emerges from the block again, it bends away from the normal as it passes into a substance with a higher speed of light. So when it goes from the slow plastic back into the fast air, it bends away from the normal. And you'll notice that the path of the light ray coming in is parallel to the path of the light ray coming out. And that will always be the case if the sides of the plastic block or the glass block are parallel to each other. That the incident ray will be parallel to the emergent ray. And as it passes into the slower substance, it bends toward the normal, and then it bends away from the normal. Now, it would be nice to have a way to remember that, and we do have a way. And this is it. And the way we remember is with lawnmowers. Most of us have pushed a lawnmower through grass. And the idea here is that we have a rectangular plot of grass, which is relatively soft and relatively difficult to push the lawnmower through. And then we have hard asphalt, like a driveway here and then the neighbor's driveway over here. And it's easy to push the lawnmower on that. It goes relatively fast for the same amount of push. So we are pushing our lawnmower kind of up at an angle here, because why not? And these represent the wheels here on the lawnmower, on the top and bottom here, and this is the bar in between, and we are pushing the lawnmower up and to the right here. Now, when the lawnmower starts to cross the threshold from the driveway to the soft grass, the right wheel is in the soft grass. And we know from experience that when one wheel is in the soft grass and the other isn't, the lawnmower is going to tend to pull to the right. It's going to be dragged to the right. So as we progress forward again, now it's going to track straight as once both wheels are on the grass, but the angle is different if we've let it go do what it does, to let it do its thing. let it move freely. So it will track freely across the soft grass, even though it's harder to push. The lawnmower will tend to go slower for the same amount of push, but it'll go straight. And that will continue until the right wheel leaves the grass and gets onto the hard asphalt. Now it's the left wheel that's on the grass, and we know, again from experience, that the lawnmower will tend to pull to our left until both wheels are on the hard asphalt again, and then it will track straight. So I'm going to back this up because it actually works pretty well as a moving thing. So we start off pushing the lawnmower at an angle toward the soft grass, and as we progress, it drags to the right, tracks straight, and then drags to the left. And we can see that the path of the lawnmower is straight. It bends toward the normal in the slow, soft grass, and then it bends away from the normal again when it gets onto the hard, fast asphalt again. So the lawnmower does the same thing that the light does as the light passes from a fast medium to a slow medium and back to a fast medium again. This, I find, is a very convenient and memorable way to remember which way it goes and why. And it turns out that it's not just an analogy, that's actually kind of the way the light behaves. It moves in wave fronts, and part of the wave front slows down and the rest of it runs ahead, and it causes it to change. If you want to see more about that, look up a video on the internet about it. Yeah, it's kind of fascinating. Kind of goes back to Huygens principle again, which we learned about in class. Okay, what about different colors? It turns out that different colors react by different amounts, and the reason is because they have different wavelengths. So the slowing changes them more or less depending on their wavelength. And this is why a triangular prism will break white light, red, green, and blue light, into a spectrum of red, green, and blue. Turns out that lower wavelengths, smaller wavelengths, higher frequencies refract more than lower wavelengths. That's not something you really need to know which is which. It's enough for you to know that the different colors are refracted by different amounts. Now, as far as our lawnmower analogy goes on this one, if this was a triangular lawn, it would the lawnmower would be pulled toward the normal as it goes from the asphalt to the soft grass. But because this side of the grass is not parallel, it bends to the right again because the left wheel gets onto the asphalt first. So again, it pulls farther to the right. So that's why it doesn't get undone when it leaves the glass or the plastic when you're talking about a triangular prism. Okay, now that brings us to total internal reflection, which is an important concept, which, as I said, is important to a future unit that we have and to our technology and our communications in the real world today. So what's the deal here? Total internal reflection. It is a refraction phenomenon. This happens because of refraction. And the idea here, I realize this is kind of a busy diagram, but bear with me here. The idea is that we have a slow substance like water, and then there's air up above, and we are shining a laser from inside the water to emerge into the air. Now, when it goes straight up, it doesn't refract at all. It just goes straight across, like pushing your lawnmower straight across from the driveway to the grass. But if we shine the laser up at an angle, then as it goes from slow to fast, it bends toward the normal, which means that this ray is more parallel to the surface of the water. And the steeper we make the angle of the laser, the more extreme that effect is. The more the ray is refracted and the closer to parallel to the surface it gets. Now, if you think about it, there has to be an angle where when we shine the laser, it's refracted so it is parallel, absolutely parallel to the surface of the water, and it's unable to get out. Now, they call that the critical angle. We don't need to know that, but that's when total internal reflection happens. So the light is literally unable to emerge from the water or the glass or the plastic or whatever this medium is down here. But energy has to be conserved. The light has to go somewhere. So what happens is it is reflected back into the water. And so that's why they call it internal reflection. It is reflected internally back into this medium. And it's called total internal reflection because it's perfect. There are very few things in physics that are truly perfect, but this is one of them. All of the energy is reflected perfectly back into the medium. Nothing emerges. There is no loss. It all stays inside. Now, why do we care about that? Oh, yes, and this only happens when light tries to go from a slow medium like water into a fast one like air, or a slow medium like glass into a fast medium like air. Only goes from slow to fast. Now, why do we care about this? Well, so this is a photograph of a total internal reflection in probably water. And they've shined a laser into the side of the container. And you can see it refracts a little bit when it goes into the side of the container. But we get total internal reflection right here at the surface because it's trying to go from a slow medium into a fast medium. And it's a very shallow angle. It's below the critical angle. So we get total internal reflection back into the water. No beam comes out at all. We were able to see the beam in the air over here, probably because they have some sort of a fog machine going to make it visible, but you can see nothing emerges from the water. It is totally internally reflected, and then it emerges from this side and goes back into the air again. Okay? Now, it doesn't have to be nice flat sides. It can be gradual curves. And as you can see, the laser beam or the light ray follows a series of straight line paths, but it's always hitting the edge at a shallow enough angle that it's total internal reflection, and the beam stays inside this sinuous tube. This is what it looks like if we have like an acrylic tube. Now, this is not very pure substance, so you can see it kind of glowing out. You can see it glowing all over the place. But if this was very pure glass, very transparent glass, the light would only come out the end. We'd be able to shine it in one end, and it would stay totally inside the fiber and only emerge from the other end. And fiber optics are capable of transmitting light rays for literally hundreds of miles. Fiber optic cables is how we communicate across the internet. Okay, I'm going to pause here and we'll pick up in another video.